And it is also, once again, we'll have this hour-and-a-half class. We'll have a break. For me, it's lunch. I think for you is evening dinner, maybe. And then we'll have another class. So hopefully in these classes, we will do the simulation of analog circuits now in this class, and then in the next class we'll do some simulations of digital circuits. I think it's an important element to understand, and it's important to like tool in your back pocket if you ever have complex analog or digital circuits. Simulate them and see what the results are. Right, so yes, that is it. Okay. Oh, as well, we will continue on with this class, with this sort of like Teams meeting. After the hour-and-a-half is up, after this class is up, I'll say goodbye and I'll just leave the session, but it'll remain open. So you can either stay in the session or log out or leave it and then come back again. It will remain open. There will not be a new invite for a separate meeting or a separate Teams link. This is the one we will be using throughout today, just the same as last time. But once again, any problems, any questions, let me know. And finally, I'm sharing my screen. Right, you should see a background person running or something to that effect. Right, so I have opened my Eagle and I'm back on this landing page. Now, obviously, landing page just means it is the first page that you open. That's like introduces you and tells you what is going on. In terms of Eagle, it'll give you the news. And then what we're interested in is actually just going to File. I don't want to open anything because I haven't really completed anything with you guys. And then just open a new schematic. So once again, the schematic. All right, let's actually close this for now. So the schematic will be dealing with mostly 4 objects in this little menu. The schematic is the circuit, the symbolic circuit we'll be creating. Board is the physical PCB board, which we'll be developing from the schematic that we have drawn up. Library are library elements, and those are where all our components live. And then design blocks, we will have a look at designing some design blocks of our own. And these are reusable circuits that we can use over and over again without having to redesign them. So open up schematic, open up this little page. The first thing that I always like to do, and I keep on telling to everybody, is open up the grid, change my grid to millimeters. I click on the display is on, so I display it. And also, I keep on forgetting to show you what this is. My alternate is very much smaller as my size there. So once again, we spoke about, so this is microns, millimeters, mil, and inch. Obviously, a mil, M-I-L, is a thousandth of an inch. You have a millimeter, and a micron is, I think, a thousandth of a millimeter. So you can go really, really small. I like working in millimeters because it is something that I understand or I'm well familiar with. But if you do create, so in which case might we work with microns or moles? Well, I'm not sure. I've never really worked with microns, but I have not designed very, very, very microscopic circuits. If you are designing a CPU board, for instance, with a ball grid array that's got 96 or 100 odd pins, balls on the backside, then you might use a micron intervals to space your elements as close or as far away as you can. But just be aware, if you use microns and things like that, just make sure that the place or the person creating your boards are able to create your boards with that small resolution. And when we talk about PCBs, we'll talk about like the design rules that companies follow. But every single company would have a a minimum size that you have to adhere to. Because let's say your company uses drill bits to drill out the copper of the copper plate. Now, their smallest drill that can remove the smallest amount of material might have a diameter of 0.1 millimeter, which is really, really, really small, a very, very thin drill. So the smallest gap or the smallest amount that you can then create your board is then 0.1 millimeters. So if you work with microns and you have 1 micron or 10 microns, then the manufacturer simply cannot produce your board. So that is why I like to work in millimeters, because for my purposes and the circuits that I design, millimeters are perfectly fine. But you might, as you progress in your journey of becoming an electrical engineer and going deeper into printed circuit boards, you might use microns. I cannot predict your future. So I'm sharing my screen again. The next thing that I like to do is I like to add a frame. So I go to Part. Usually if I add on parts, it takes a little while to load in. I click on Frame, and these are all the different frames that I can choose from. This is an A5 frame. I don't want A5. I don't want letter. It all depends which sort of like which format you're working with. So let's say I'm going to be printing this out on an A4 paper as part of a report or some sort of design schematic, then I will most probably use my A4 version 1 frame. And I usually like the landscape, so I set it down on my origin. I press escape again and just cancel the placement. I can zoom to fit of my circuit. If I click on zoom to fit, it fits in all of my circuit here. Once again, I can search for elements that I want a resistor. Now, very importantly, if I search for the term resistors, meaning the plural of resistor, it will not find the correct, it will find these elements which has the word resistors in it. So you have to be very specific for what you are searching for. If I'm looking for a resistor single, you have to search for a single resistor. Redo the search and now everything comes up. Mostly I'm interested in my basic resistors. So either the US or the EU. Let's go with the US because I like the squiggly lines bit. And then the description has to do with the package of those resistors. So once again, this is the symbolic symbol of the resistor. And then the footprint, which is the physical footprint or the physical elements that will be found on your board, where green is the pad and there are the holes for your component to fit through. And this is a standing upright or a vertical resistor. And I like these ones. And once again, the description, it's a type 0204 resistor. And then, as always, if I search for 0204, I will come up with these results. Now, 0204 is the package description. As we spoke about, all resistors, all components come as certain package types on packages. So what we are then looking for is that we will have to have a select the correct components and then make sure we buy the correct size components. either we buy them or make sure that we have them in stock. That is why it's very important to make sure that, so this is a 0204 and that is a 0204 resistor. So I can confidently use this resistor knowing that it will be the exact same one that I would like to order. So I can place it down simply by clicking. I can right click and then it rotates my resistor. And I usually like to create circuits like this. Press escape once again. Now, as we have seen, our resistors are 1, 2, 3, and 4. We can give them new names, but these names will have to be unique. And we can also give them values. 100K. This might be a 10 mega or a 10 million ohm. And this might just be a normal 100 ohm. And this is a 250 ohm resistor, for instance. Now I can mirror my components. I can move them. I click on move, click on the center of the resistor where you have these arrows, and I can move my resistor around as I like. I can also do a group move where I group my resistors. I click on move, right click in the screen, and I can click again on move group, and then I can move a group of resistors. As well, I can copy and paste and also delete some resistors if I so choose. And I can also connect them to a net. Connecting my resistors. So I start from the connection, one of the connection points. It lights up as a green circle. That means I can connect from there. I can click. I can also have different styles, which will come in a little bit later. And so on. And then I can have some sort of connector. Now, once again, we have sort of like found out that a lot of these connectors, so this is from a company called Adafruit. And what connectors do I want? Let's have a look at all of these. Coaxial connectors, a connector from Conrad, a German type connector, all these different types of connectors I can choose about. So how do I know which one I should use? Well, with PCB design, either you choose the connector you want from the PCB and then look at the description and find that specific connector, or you buy the connector and then look for the specific connector inside of Eagle. Now, a lot of manufacturers will have their own Eagle libraries that you can download with all of their components already as footprints for you to use. Most big companies would have the libraries that you can simply just download and use. And they do this because they want you to buy the components from them. So then they create their component libraries. You can download it. Like I downloaded the Adafruit library, and then you can use it to design your components with their board, design your board using their components. So, right. In terms of components, I'll go back to my screen and I'll just select an Adafruit component, a connector, excuse me. And it is a 1x4 connector. It looks like this. So either I can rotate it or I can simply click on mirror and mirror it like that. So what does that, what's the difference between just rotating and mirroring? So let's have a look. So I have this component here. I want to rotate. That is the difference between mirroring and rotating. Now, if I mirrored my component, my first pin is at the top, and if I'm just rotated my component, it is pin 1 is at the bottom. So how does that work? Now, you have to think a little bit three-dimensionally. So if I have my component like that, mirrored will be just like that. And if I've rotated it, it'll be at the bottom like that. So that is how it works. So you have to remember the difference between rotating and mirroring components. Now with these connectors, doesn't make a big difference. Sure, it doesn't. But if you have components like integrated circuits, like ICs, microchips, that the pins have specific functions or unique functions that are different from the other pins, you have to bear in mind how you rotate or mirror those specific components. And as well with this, so like one row component, I can mirror it quite easily. But if I have so like a dual inline package with 2 parallel running pins, I can't just mirror that because the pins are only on one side. So if I mirror it, the pins will be on the other side. And these are all things that you have to think about when designing your circuits. Right. I'm sharing my screen again. So what I'm doing is as I'm going along, I'll just be describing what I do. Okay, so I've decided that I like the pins like this. So I can then connect up whichever pins I like to my connector. And then once again, if I have a connection like this, here, these 2 nets, as we call them, are not connected. So if I click on info, I click on that little net, it will highlight, don't know how clear it is on your screens, that specific net and give me its net name. So that's N$2, which is the computer generated net, but I can change that. And if I select this net, this is N$6. So if I want to connect the nets, I can create a junction, place the junction down where those 2 nets intersect. And what can I do then? I can tell them, connect the segments, and then I have to connect. What name should I give them? Let's give them all N$2. So now, this is net N$2. This is all N$2, and I can easily check it by adding a label. And you can see wherever this label is touching, that is where the net is. So I have used a junction to connect my net. Once again, not once again, let's create a message. I can create a message, and this message is now on the nets layer, meaning that if it is, it will be created in copper. If I go to the next stage, I can change the nets. So far, the 2 nets that we are really interested in is the nets where we have our connection and also the names. So now it is on the names layer. What does that mean? It means that it will now be included on the silk screen. And remember, the silk screen is that white writing that is on top of our solder mask. So all the white writing or gray writing, whichever color you see this as, it's probably more a light gray than anything, will be included in the specific silk screen, so that I can pass along any information that I would like my the person assembling my circuit to have. Okay, so that is a basic rundown on how to create basic circuits. Now, I can add in any components that I would like to this, but personally, let's start with the our whole circuit. So I've just created a new circuit. What did I do? I have just selected everything as a group. I can move my group, right click, move it, or I can simply select my group once again and right click, delete everything. So now we'll start with simulating basic analog circuits. So what do I mean by analog circuits? Well, for this instance, an analog circuit is mostly circuits to do that has to do with voltage and current, and it's mostly made up of an RLC circuit, so resistance, capacitive, and inductive circuits. We also have some transistor elements, but generally we do not have any digital elements like logic gates or microcontrollers. So think of this as like a simple circuit. I have a simple resistive, capacitive, or inductive circuit, and then I want to see what happens in my specific circuit. Now, bear in mind, EagleCAD has relatively basic simulation capabilities, but so I'm sharing my screen once again. As we spoke about, it uses a system called SPICE, and I googled what SPICE means. I'll bring that up to you guys. Oh, wait, no, that's not going to work. SPICE is simulation program with integrated circuit emphasis. So it's just an integrated circuit simulation. So how can we do that in, let's click on this. How can we do that in Eagle? So all the things that we need, let's clear the search, are in a file called ngSpice. I'll just, I passed it, ngSpice. So ngSpice, I'm just typing something. Right, so yeah, I'm sharing my screen. Why don't I unshare my screen? I don't know. So in my libraries, there are these two folders named ngSpice Digital and ngSpice Simulation. So simulation, yes, that is exactly what we want. So contained within this folder are all the different simulation elements that we can use in EagleCAD. We have an ammeter, so it measures current. We have a NPN bipolar transistor, PNP transistor. We've got a capacitor, a linear current controlled current source, a linear controlled voltage source, an independent current source, a diode, and then we have a couple of MOSFETs, a couple of voltage controlled, a sinusoidal, all these trigonometric. These are all FN stands for function controlled source setup. So we have anything that you want to have a certain function injected into your circuit, like a tan, a sine, logarithmic, all these exponential cos, arctan. If you have any circuits that need one of these volt, every single simulation needs a ground. I will speak about why a little later. And I have my general inductor, an LED, a non-linear dependent source, an operational amplifier, a resistor, a transformer, and a linear voltage controlled cutter source, and a linear voltage controlled voltage source, a simple voltage source, and a voltage controlled switch, like a relay, for instance. So what are we going to be creating? Well, let's create just a simple resistive circuit. So I click on resistor, I click OK, and I place down a couple of resistive elements. Now, if I have resistive elements, I need something to control them with. Usually I like just using a simple voltage source. So this can be just a battery, a laboratory voltage source, anything that you want. And every single analog simulation needs a ground. Why does it need a ground? Well, it needs to, basically what this software is doing is you've added in those components, and those components are then transferred to mathematical equations. So it creates those equations, and then it solves them in terms of voltage or current or whatever you are needing at that moment. But it can only do that if it has a reference. Remember, when you're dealing with voltage, you always are measuring from a reference point. So when you are measuring voltage, for instance, with a multimeter, you will always have two nodes measuring, and it will always be in reference to one of those nodes. And that's what we're doing here. So we're putting down a reference node to somewhere which makes sense for us to take our measurements from. In this case, I'll just connect my ground. I've shared my screen again. I'll just connect my ground to the negative part of my battery. So let's connect up our circuit. Making sure everything is nice and connected. And then making sure that so it'll ask you merge this net into net 0. Yes, because this is now my ground node. If I want to have this a little bit neater, just move it around, and it is still connected. Now, for simulations, you need very specific values. So let's create some values. This will be 100 ohms, 200 ohms, 300 ohms, and let's have it 400 ohms. Why not? So now I have my resistance network set up, and these are 100, 200, 300, 400 ohms. I then click on my analog source setup, because this is an analog source. I click on my source, and it will ask me, do I have a DC value, AC value, and some sort of transient function? No, I do not care about that. I only care about a 12-volt value. It's not an AC, it's just DC. So now I have everything in my circuit set up. I do not need, we'll go over what these are in a second. We'll click on simulate. Now simulate gives you a couple of simulation types. If I have an operating point simulation, it will around that specific operating point. So operating point means it takes one specific voltage, and then that voltage is the voltage that it's giving you. So let's do that. Let's simulate, go simulating, and it'll give you these values. Now, these values, it gives you these variables, and then it'll solve these variables in terms of voltage and current. It's not really useful. So if we go out, we can see that it gives us, I don't know if you can see this quite clearly. Let's move these values around a little bit. 12 volts. No. So let's just zoom to fit. So this is the result of my simulation. Okay, let's just do this a little bit easier. Options, user interface. Let's just change my schematic to white so that you can see this in a better view. Okay, so let's. So in this net over here, I've got a sum total of 12 volts. So this makes a lot of sense because it's on this side of the battery. If I take I'm basically measuring the voltage across these elements. And then after my voltage goes across this resistor, it drops to 10.8 volts. Then it drops to 8.4, drops to 4.8, and then drops again to 0. So this should be the 0 volt net because it's connected to ground. So now I can calculate the voltage drop 12 minus 10.8, and it calculates the voltage drop. As well, this is the current circulating through my circuit. Now it's as a minus current because I think current actually moves in this direction. Don't worry too much about that. It is the current is 0.012 ampere, and it's exactly correct because we have got a series circuit. 100 plus 200 is 300, plus 300 is 600, plus 400 is 1,000 ohm circuit. Voltage divided by resistance gives me current, so it's 12 divided 1,000 equals 0.012 ampere. So that now gives us our total current. And as well, if I want to know the voltage drop across R1, it is 12 minus 10.8. So the voltage drop across my R1 resistor is what, 1.2 volts across R1. And we've created a simple simulation. Now, relatively simple, relatively easy. We can also add in certain elements, not just the resistive elements, we can also add in capacitors, but then you will have to understand what is happening in your circuit. So let's add in a capacitor here. Now, unfortunately, we will have to delete some elements to be able to fit in this capacitor. We can't just insert it, drop it onto the line and hope it connects by itself. So let's add in this capacitor. Let's give it a value let's say 100 nanofarads. We do simulation again. We update the netlist. So what does that mean? It means that if we've added any additional elements to our circuit or changed it in any way, we have to update our netlist and tell our simulation circuit just to redo the calculation so it does not give us the same element again. So let's do the operating point once again. We simulate, it simulates, and it gives us these values. So what is going on? My simulation tells me I have 12 volt, 12 volt, 12 volt, 12 volt, and on the other side of the capacitor, I have 0 volts. What does that mean? Well, now it comes back to that you have to understand what your components that you're simulating actually does. So what does a capacitor do? A capacitor basically charges up, and then once it is full of charge, it acts as an open circuit. So it cuts off the flow of electricity. Therefore, you have 0 amps running through the circuit, and you have 12 volts on the one side of the capacitor, and then 0 volts on the other side, because that is what the capacitor does. So this is why I keep on saying that you have to be very, very, very careful when you are dealing with these elements. You have to understand what is happening, because you might have done this simulation, added in a capacitor where it does not belong, and then somehow that capacitor or that circuit gives you these results, and you think that, well, the program is wrong. No, the program is right. It's doing exactly what is what we told it to do. So what can we do? Well, we can run another type of simulation. To do that simulation, we add in voltage probes. I've shared my screen once again. Up top here, we've got a voltage probe. This is the voltage probe. I can click on it. Let's say I click on the voltage probe here. And let's say we click on the voltage probe here. No, actually, I don't want that voltage. I'm more interested in this voltage. So now I can redo my simulation, but I'm not going to do an operating point, because operating point just takes one voltage value and then gives me all the values around that point. What I'm more interested in, let's not deal with DC sweeps or AC sweeps. I'm interested in a transient simulation. So what does transient means? It means it takes a certain time. So this is a more realistic type of circuit, because it starts and it calculates all the values until it gets to a steady state. So it basically what it does is it calculates all the value between 0 and then between once it gets to the operating point. Because if you have an electronic circuit, if you flick the switch on, all of the values of all the components and everything are not instantaneously their final values. It takes a while for voltage to build up in a capacitor. It takes a while for a current to flow. Very, very short, mind you, but it does. So now we're going to be looking at a second simulation called a transient simulation. It'll run from 0 seconds up until 1 second. It just update our netlist. I always click on update netlist whenever I run new simulations, so that I don't forget to do it when I actually have new components. So let's simulate and see if something has changed. No, nothing has really changed. So this is our 2 lines. So this is the 3 values that we have calculated. We have the current, which is 0, voltage, which is 12, and voltage, which is 0, basically 0. Minus 16 is relatively 0. So once again, our nothing has changed. So let's change my stop time to something a little bit quicker and see if there's any change. Now, there might be something happening here at a very, very short time, but we have to change the time once again to see what is going on. Now, something is happening. Right, let's change it again and see if we can zoom into what is exactly happening. So the reason why we're seeing something here is that it takes, let's create this. And that's a little bit too much. Right, let's take out a 0. Right, configuration, let's take out another 0. Too much. Okay. So let's just keep it at this one for now. So what is happening? So what we're seeing is the capacitor charging, and then as it is charged, when it is charged, let's just add in a 5 there. The voltage drops to 0. So that is what we are seeing. But like I told you, it is the simulation software is not really that great. It can't really zoom in on that little charging, but we'll create a couple of circuits. We can actually see that charging and discharging a little bit easier. Right, we'll take a short 5-minute break. I'll go make myself some more tea, drink some water, do what you have to do, and then I'll see you in 5 minutes, and we'll continue on looking at some simulation elements. Right, see you all in 5 minutes. 5 minutes. So let's continue on with simulating circuits. And then just the point that I would like to emphasize and that you understand is that the simulation is just what it does is it breaks all your components down into equations, solves those equations, and gives that answer back to you. So if you make a mistake in your circuit, like I did by inserting a capacitor in series of the main current branch, then yeah, things won't end that well because my simulation tells me results, and I think that is wrong, but I made the mistake. So when you are simulating circuits, ensure that what you are doing is correct. Otherwise, yes, it might end badly. So I'm sharing my screen again. Now with the simulation software, a lot of the times things go wrong. And it is always good to sometimes just reset everything. So let's close it. We'll open up a new schematic. Once again, I set my millimeters. I keep on forgetting to show you what this one does. Right. I add in a frame because I like to frame everything. As well, this is actually probably a good question. Which color is better, dark or light? So I'm just asking a little question. Should I leave it on the light white background or the black background for you to see better? Just somebody answers whichever ones you can see better on your screens Because for me, it doesn't make a difference, but it might make a difference for you. So I'm sharing my screen once again. So I'm sticking with a white background for now. If the black background is better, just let me know. Right. So we go to our main folder. I like to then navigate to the ng spice simulation folder. Let's start off with a voltage. We add in a voltage. We add in a couple of resistors. Because another class that I used to teach was also sort of like introduction to electronics. And in that, we had to create a couple of resistive circuits using nodal analysis, net analysis, to try and figure out what the specific values of circuits or voltage across certain elements were. So it is now, I'm creating just a random circuit. A random resistive circuit just to show you how nice it is now that we can use EagleCAD for those. So Daisy, is that connected? Let's make sure that it is connected. Turn info, highlighted in .5, in .5. So it is connected. Great. And then just to be nice, I'm connecting this circuit in such a way. So let's give a couple of values. That is 100,000 ohm, for instance. That is just a normal 125 ohm. 349 kilo ohm. 1 mega ohm. 250 ohms. So I'm just giving random values. I haven't, this is just a random circuit that I'm creating. I just want to illustrate something. So what am I trying to illustrate? Just how easy it is to simulate a relatively complex circuit. So analog source setup, let's give this a 24 volts. So you might get the question, and the question might be, okay, so we have this circuit. Calculate all of the voltages running through all of these branches. So that is relatively complex when you have to work it out by hand, but now we can just simulate it. Click on simulation. Oh, I made a mistake. No ground known in netlist. Okay, so I need to add in a ground node. Of course, remember I told you, you need to have a ground node connected somewhere. So I like to connect my ground node to the negative pole of my circuit. Yes, and now this whole net is 0 volts because it's connected to ground. Now I can continue simulation. So I don't really need transient. There's no transient elements. I can just do operating point, update my netlist, and simulate. Now we have all of these values. So all of these values now are available to us, and they are not really that nice to read. Oh, I don't want that. Nope, I want that value. So we now have all the voltage values. So I can calculate the current running through this, but I'm a little bit lazy. I don't like calculation. So what do? Well, I can add in another element of my ngSpice, and it can be an ammeter. What does an ammeter do? Well, it measures current. So I've decided I want to add in my ammeter in this element. Now, ammeters are unfortunately really big. Don't worry about it. Let's connect up my ammeter and connect it to this node. Simulate. So now I know that running through that specific ammeter is a very small amount of current. Yeah, that is it. Is a very small amount of current in terms of 0.00256 amps. So now I know the voltage running through this element and also the current. Now I can do this for every single element in my in all of this. So this is not a is not an extremely complex circuit. I mean, I can calculate this not easily by hand, but I can calculate by hand if I would like to. But you don't have to. Just use the simulation. If you have a resistive circuit, just simulate it. And if you would like, so the basic simulation gives you all of the voltages in the specific nets. And then you can use an ammeter inside of that circuit to then see there is what the current flow through that circuit is. Now you can also do this for AC circuits. Just change your source to an AC source. I'm not going to do that now. I'm going to move on to something else, but the main method remains the same. Just create a circuit, simulate it, and get the results. Relatively easy, relatively simple. Right, I'm sharing the screen once again. And now when I start with a brand new simulation, I tend to just close this down and then add a new or start a new schematic. Why do I do this? A lot of the times the program gets a little bit confused and remembers the old simulation results, which is not exactly something that I would like to have it do. But yeah, it happens. Okay, so first things we always do is just add in the frame. Like I said, I like this frame. I add it to my start point. Now, what would I like to do? So there's a circuit that I really love. Well, if you can have favorite circuits, this is probably one of them. It is a, what's it called? Oh, it's sort of like a multi-vibrating circuit. So what it does, you have two LEDs, you have 4 resistors, a couple of capacitors, and then you have 2 transistors connected to 12 volts. And what should happen is that these LEDs should light up. And it is all to do with the transistors switching on and off as soon as the capacitors are finished charging. So this is very, very, it's a common circuit. I won't be surprised if you've run across this before. But basically, as it does, the resistive and capacitive elements, as one capacitor is fully charged, it switches on the one transistor. the one LED starts working. As it starts working, the other capacitor starts charging. And then as it's charged, it switches that transistor on, and those two LEDs should switch on and off in a pattern designated by the resistance values and also by the capacitor values. So let's create the circuit and see what it looks like in simulation. I think it's interesting, right? I'm sharing my screen once again. I will just, can I do this? Hopefully I can. And this works. I hope so. I'll copy that like GIF into the chat so you can download it maybe and have a look at and play around with it as well, because I think it's quite interesting to see that circuit. Right. So that is right. So as you can see from the circuit you're looking at, we need 4 resistors. So let's get 4 resistors out. So once again, go to our components. Let's clear this out, press enter again, navigate to my ngSpice simulation, and then navigate to my resistors. Okay, let's just do it in the middle. I like my resistors to be upright like this. Right. I then need 2 LEDs. Let's go to LEDs, rotate them so they're in the correct direction. What else do I need? 2 capacitors. Now you might see that the capacitors in the image are polarized capacitors. They don't really need to be polarized capacitors. We don't really have polarized capacitors. We only have simple normal capacitors, but these are the ones we need to choose. So let's add in 2 capacitors. And then finally, we need 2 transistors. In this case, an NPN transistor. So this transistor be there. And as you can see, this transistor, I can rotate as much as I like, but it does not add up in the correct orientation. So what I'm going to do is I'm going to mirror this transistor. So I click on mirror, click on this transistor, and it mirrors next to perfectly. And now we just check that we have all of the elements that we like. Yes, resistors, capacitors. And now we just make sure that everything is nice and neat. Right, so now we connect up my circuit and then we will look at powering it. So these resistors are all connected in such a manner like so. We'll add in our power source in a second. The diodes are in series with these 2 resistors, and then they are again in connection or in series with the transistor. The bottom part of the transistor, oh, that is not connected, is then connected to the ground connection. I would just like to see this again. Right. I'm following this circuit diagram. This one works slightly better, but but we'll do both and see what the difference is. So with this connection, my circuit is connected there. And once again, I'm just following my circuit diagram. And I don't think there's a connection. So let's just connect it up there. Connected up the diode. Now I can use this connection and then my resistors connect here. Oh, that does not seem like it's connected, so I click on my junction, make sure these are connected, and then I add in my voltage source. My voltage source I can add in on this side, and my voltage source. And then we need a ground as well for the circuit to work. So we have our ground connection there. Connect up our ground to our net supply. And now what is left, we need to create our values. So for these resistors, we have 1,000 ohm, and these are just protecting our diodes from current. 10,000 ohm resistors. And our capacitors are 100 microfarad. 100 microfarad. And then my power source, analog source setup, is a 12-volt source. So now we have our circuit set up. How do we know when these diodes are switched on? Well, we can add in ammeters, or we can simply have two voltage probes, checking if voltage is flowing through these elements. Right. And then let's start our simulation. Operating point does not really work. Let's go for transient. Let's take it up to around about 5 seconds. So why won't operating point work? Well, this is a circuit with capacitive elements, so the duration of time that it takes is relevant. So we simulate it, and we have a circuit like this. Now, in this circuit or this plot, we have 3 distinct signals. So we click on signals. We have current, voltage of the one diode, voltage of the second diode, and then the current. And let's deselect the current. You click on signals. You select the signal that you want. Apply changes. So what is happening? How do we interpret this graph? Well, as you can see, the voltage builds up across the one transistor, actually, and then it suddenly falls while the other one starts building up. And it switches between the two. What effect will that have on our diode? That means that it is then switching on and off. So that is how we can interpret this. And now, how does this make our life easier? Well, you can have a simple equation that can calculate the on and off times. I mean, for this, let's just do the simulation again. We can see that it takes roughly one 0.6 seconds for that the one diode is on and the other one turns off. But now we can start playing around with values. So we can play around with the one capacitor's capacitance value. So this is V5. Click our simulation again, update our netlist, and run the simulation for a second time. Now, what do we see? Well, let's just have take away the one signal which is bothering me. Well, we can see that the one diode is on for twice the amount of time than the other one. So the one capacitor takes twice as long to charge the other one, meaning that the one diode is on for twice the amount of time. So we can play around with all the values in our circuits, figure out what is the best course of action. Now, I should also add in this one circuit which I have created with the values. Oh, goodness, it's so awkward. I'm trying to drag in something. With a small graph of the circuit that I've just created. Now, the eagle-eyed among you might see like, well, these are two different circuits. And what do I mean by that? Well, I'm just opening up both of them so we can have a look. One circuit and this circuit. I'm sharing my screen with you guys so you can have a look at what I'm seeing, because I forgot. So the one circuit, the connection is slightly different than the other one. So the configuration that I use is the one here on the left, and the one on the right is this GIF version, which we'll try just now. So the one on the left, I created, and the one on the right is the one I got from this GIF, and you can see the connection. Oh. Capacitors are kind of in the same elements. Yeah, it's just the capacitors are just moved along a little bit. This capacitor is moved down here, this capacitor moved down here. So they are exactly the same circuit. Sorry, my mistake. I initially thought they were different, and I was wondering why I gave you two different circuits, but they are actually the same. So this capacitor, C1, is just moved down this circuit here. See, that's capacitor. It's just moved down there. And this one is just moved down the circuit there. So they are exactly the same circuit. And we can now play around with different values, different circuits to get the correct values. So what does this really help us? Well, if we have this circuit then simulated to the extent that we would like to have it, if we change a couple of values, simulate again, then we can figure out if we want to build this circuit. We can then substitute our simulated components for real components and then be fairly certain that our simulated results would carry on to our real PCB results. And I mean, this is just like a fun circuit that I like because there are flashing lights and there are different elements to create, and it's just a fun circuit to create. Now, what I would suggest that you guys do is that probably after this class or after this afternoon or this evening's class for you guys, try and recreate this circuit in EagleCAD yourself doing the simulation. This is not homework. This is you doing things for yourself. So you recreate the circuit, which I have given to you in the chat, download it. I'll also email it to you guys. Use it to create the simulation and then play around with the simulation so that you become more comfortable. Because it's a lot easier creating these circuits in simulation than calculating all these circuits by hand. And as we spoke about, all these tracks or nets, as Eagle called them, will translate into the tracks we use for our PCB design. So we use simulation like this so that we can calculate or see how much current and voltage runs through certain elements of our circuits and runs through certain elements of our components. So what does that do? Well, for one, it means that we can ensure that the components we are using can handle that amount of current, voltage, and or power, and also that the track width, how thick those tracks are adequate for our circuit to operate in the way that we would expect it to be. These circuits are really useful. I personally feel it's useful, especially if you have a subject where you are dealing a lot with these circuits. Personally, for me, I'm very bad at drawing things by hand. So whenever I used to write a report for other electrical engineering subjects, I would create my circuit in Eagle or something like that, and then cut that circuit and insert it into my report. So these Eagle simulation things are really useful, not just for simulating the circuits, but actually using these circuits in reports. Now, another thing that I have failed to mention just a little bit is when we're talking about the grid, we have this size and the alt size, which is smaller. So what does that do? If you click on alt, my grid size changes. So here my grid size is 1 millimeter, excuse me, meaning that these blocks are, the difference between them is 1 millimeter. If I press Alt and hold in Alt, you'll see that this grid now changes. It now becomes 0.01 millimeters. So what does that do? So if I'm moving a component, let's move this component. You can see if I move it, it moves according to my grid. But if I press in Alt, you see I can move it in between my grids according to my very, very fine subgrid. So if I want to move my component between my grid lines, I just press and hold Alt, and it moves in between those lines, or I can just move it according to my main grid. So that, once again, I set with these alternates, and I can move my grid. If I press Alt, the grid changes, and I can move my elements in a more like smoother in between those grid lines. So why does that become useful? Well, if you have a schematic with hundreds of components, which I did have on multiple occasions, every single millimeter counts. So even if you just add in or shift a component just a couple of factors of a millimeter to one side, you can use that to just create a more nicer element. Okay, so what can we also do? Well, so the reason why I have this is, okay, so let's say I can save this, save as flashing LED. I save this as flashing LED. It gets updated, flashing LED, gives you the time that I saved it last. And I can also now, let's say we want to print this. Now print this, Microsoft Print to LED, paper, A4, landscape. I can print this. Let's save it as flashing LED. Let's save it on my desktop so I can find it quite easily. And now my design is saved on as a PDF. I'll just have to find it. There we go. And now this is the PDF is a little bit slow. And this is my element or my circuit that I can now give to people. So that is why I like having the frame, and I insist that you use the frame, because whenever you need to show your circuit or send your circuit to somebody, you send it on inside of an A4 frame, and that gives the person receiving your circuit an idea of the size or the scale that you're working with. And it also just looks neat because the name is there, the last time you worked on it, and then how many sheets are also on there. And you can add in any information that you would like to have on the circuit. So that's why I like having the A4 frame, because you can save it or print it out as a PDF, and it is all contained within that A4 frame that fits onto or inside of an A4 frame or an A4 A4 frame, A4 piece of paper. Another thing that I probably have to talk about is that, nope, is that let's say I have my schematic, I can still add in elements outside of the frame. I can have my circuit pretty much as big as I want. So the circuit can be massive. It can be absolutely huge, but I do not recommend having it so big, because now it becomes difficult to navigate in between these little elements, because the navigation is not really good, because you can basically zoom in and move these buttons here. And then if you have a zoom to fit, remember it zooms in on all of the components connected here. So I would always suggest that you work within the A4 frame, because it makes it a lot easier to actually see what is going on. Right, we're coming up to our little, well, not our little break before we carry on with the next class. So, I mean, this is the introduction into the simulation of analog circuits. Now, I just did it with DC components, but you can swap the DC source for an AC source, no problem. We might actually do that really quickly when we get back. And then we'll start with digital circuits. It works roughly in the same way, not a problem. Right, I think I'm going to end this class right here. I'll send you an email. No, I'll send an email at the end of the next class with like the circuits that I would like you to practice. And then, right, have a wonderful break. Have a nice break. And see you guys. I'm just going to have a look and see when you're supposed to be back, when you're supposed to start the class again, just so we are all on the same page. So you're looking at me, looking at my screen. Excel sheet, yes, there we go. I'm sharing my screen for the last time. And we are busy with analog digital systems. So our next class starts at 1900 hours for you guys.